Okay, thank you for the introduction. And first of all, is this good? I have to stand here. First of all, I want to thank the organizers for giving me the chance to present our recent work here at ICAP. And my entire talk is actually brand new, and nothing of that is published. And we were really excited of seeing actually molecular physics, like very exotic molecules. What those are, I will show you in a second, in our quantum simulator that is designed for studying many-body physics. Okay, so let me start with explaining you why the molecules, the binary molecules that we are seeing are actually very exotic. So let me remind you first what like normal diatomic molecules are in the simplest picture, really. So let's first say I draw here a standard Lennard-Jones potential, and then you have an attractive part which comes from the van der Waals interaction, and you have a repulsive part. So what makes up the repulsive part? The repulsive part comes actually from Pauli exclusion, Pauli repulsion, when those two atoms are actually ramming into each other, when the electrons start to overlap. That means basically, okay, perfect. That means basically that the equilibrium distance of those molecules is always pretty close compared to their the size of their electron clouds. In other words, basically, those molecules, they are bound basically by orbital hybridization when they share basically an electron. This is going to be completely different with our Rydberg molecules, but now let me go along the line from basically normal ground state molecules to Rydberg ground state molecules. So those are already molecules that are quite long-ranged. And they are basically bound by, you can say, the collision of the Rydberg electron by a ground state atom that sits within the wave function of that Rydberg atom. So it's still direct contact, if you wish, between the electrons of the two constituents, and they have been studied beautifully experimentally in the group of Tillmann-Fau in Stuttgart around 2010, let's say. Good. So now, what are Rydberg dipolar bound macromolecules? Those are really huge dipolar bound molecules, and I think the distinguishing feature is really that there's absolutely no overlap between the electron clouds. And how is that possible? You will see it in a minute. That's basically because of the repulsive part comes from a different mechanism, and the binding over the whole range, it's a pure van der Waals, if you like, or a pure dipole-dipole electrostatic binding. And the energy scales and length scales, just to give you an idea, the Rydberg atoms that we use are roughly 100 nanometer in size, and we see molecular binding on a distance between two of those at a scale that is 10 times longer than the size of that atom. And those actually have been seen, or first indications of their existence have been seen already in experiments in spectroscopy, where they saw some signals that could be explained basically by theoretical potential calculations that should predict basically those macrodimers at these positions. Okay. So far for the introduction. Let me give you a quick outline of the rest of my talk. I'm going to explain you a little bit the binding mechanism of those exotic molecules. Then I'm going to explain you why it is actually good to use an ultra-cold quantum gas microscope to study maybe molecules. I will talk about, in inverted commas, in this audience I have to be a bit careful, precision spectroscopy that we did on those molecules, and finally show you how we actually can exert directional control over basically the excitation and the direction where we prepare those molecules. Okay, so what is the binding mechanism? The binding mechanism ultimately comes basically from the dipole-dipole interaction between two Rydberg atoms, and that's basically standard dipole-dipole. So we have some interactions that fall off with 1 over r cube, and so just two dipoles, and there's an intermolecular axis, or a separation axis, and the interactions are typically anisotropic with respect to that axis. An example for that is I believe what Antoine, I was not there in Antoine's talk, but I think it's basically the basis of his flip-flop interaction, where you basically have a Rydberg atom with s orbital symmetry, a Rydberg atom with p orbital symmetry next to each other, and they can resonantly exchange positions, and that comes basically by this flip-flop dipole-dipole interaction. So you can understand that basically in this, in a stress state picture, that basically those first degenerate states, being the atom being left or right, basically become split by the dipole-dipole into an antisymmetric combination and into a symmetric combination. And that picture is going to be important to understand in a minute, those potentials. And another thing is important, basically, between equal states, so if I have two Rydberg atoms in the same state, I don't have a direct dipole-dipole coupling. Yes? So how do these states interact? These states interact actually by van der Waals interaction. So how do you get van der Waals from dipole-dipole? It's basically second-order perturbation theory. So I have dipole-dipole coupling with some intermediate state and back, and I basically pay an energy price that is called in this business the Förster effect, the detuning of this ingoing energy to the intermediate state energy. And because now I have two dipole-dipole, so this 1 over r to the 6. And there's actually a special case, and that is actually when these energies here become degenerate. So if I have a dominating state that exactly matches the energy of the ingoing state, I have something that's called a Förster resonance, and I basically recover effectively resonant dipole-dipole interactions here. Okay, now we are here that I can draw a cartoon of the binding mechanism of the macromolecules. Assume we have two Rydberg atoms in the p states, so that's the pp. And now let's say we have a dominant dipole-dipole van der Waals coupling channel, an SS state just below. So what happens basically, dipole-dipole interaction basically hybridizes the two states and pushes them apart in energy. Now let's go a little bit more complicated and add another pair of p atoms here. But now the SS pair is above. And that means the denominator switches sign. And what happens now is that this pp pair is pushed down. And you can guess already what happens. I can write this now basically again as effective states. And those states actually in the crossing are then again dipole-dipole coupled. And the Förster resonance happens here because I'm now here degenerate with those two states. And I basically get a coupling. And in this upper well of the coupling, I can support bound states of this Rydberg macromolecule. And you see already, this has nothing to do with the size, basically, of the electron cloud of this molecule, which can be arbitrarily much smaller than where this potential well emerges here, basically. Okay, so let me come to the experiment. So what we have is we have ultra-cold atoms in an optical lattice. The lattice is just giving us a regular array of well-defined positions for those atoms. And what's going to be important is the lattice diagonal direction. So nothing here is about hopping in this lattice. It's all about electronic excitation. But what is going to be important is this diagonal. And then we can see basically atoms one by one using our quantum gas microscope. You will see a picture in a minute. Okay, then we excite to the Rydberg state using single photon UV excitation at roughly 300 nanometer, and we're going at the moment to the 35p state. Why 35p? Because of that matches this diagonal lattice distance. You will see also that in the next slide. Just to give you a number here, coupling, we have something like 2 megahertz bare single atom coupling to this on this transition. Then how do we do the detection? That's an image from the quantum gas microscope, and we can identify basically single atoms. So if you look here, this is a single atoms. We have an algorithm also to reconstruct single atoms in dense regions that you see here. But what you see now also here, there are some dark spots. So we can detect, of course, missing atoms, and the missing atom we know actually is a Rydberg atom, and by that we can detect them almost one by one. And just to introduce the geometry, the lattice, this Rydberg excitation laser, it will come from the lattice diagonal. That is also going to be important for the control of the directionality in a minute. Okay, so here is a little bit more complicated than my cartoon, realistic picture of the energy landscape above this 35p1/2, so that's the one that is the interesting state here. And here I show you basically two molecular potential wells that emerge, and one actually has antisymmetric electron spin character, the other one symmetric spin character. And I want to first show you that actually we can select the initial state basically to exclusively couple to one of them. So how do we do that? Basically, we assure that our initial electron spins are fully aligned by going into a stretch state, or that they have both components being aligned and anti-aligned. So in that case, basically, we expect that we can only couple to the symmetric. In this case, we expect that we can couple to both. So let's see what the experiment says. So we do now spectroscopy. So this line here is this lattice diagonal. That's the distance here. And we go up here, we scan basically, what do we see? In the case where we are in the symmetric state, so remind you there's no symmetric potential here, we see basically nothing. If we are in the antisymmetric state, we see basically losses below this well here, and then we see basically a high atom number that comes back to the symmetric case, so nothing happens there as well. We can go a bit higher, we can go to this tip. You see the blue signal, symmetric one, doesn't show anything. The red one shows already actually bound vibrational lines of the molecules we're going to talk about in a minute, and I show you in more detail. We can go even higher to the onset of this symmetric potential, and you basically still see actually the molecular lines actually of this one here, and then we see also the signal in the red one of this one, because we have a symmetric contribution here, but now also the blue one shows a signal, because of this is now basically a symmetric state to which we couple. So it looks already we perfectly well understand and can probe this potential landscape. So for the rest of the talk, everything is about this potential well. So here's basically our spectrum, scanning the laser from redly tuned towards this two atom asymptote fluidly tuned, and we see basically nothing happens here, and here we see a forest of resonances. We can zoom in there, and we see a nice series of something like 70 vibrational lines, each and every one resolved of those Rydberg macrodimers. We can further zoom in, check the line width of, let's say in this case, the first line, and that is something like 150 kilohertz, which is roughly twice of what, or square root 2 of what we have for the single atom line. So that says already that those Rydberg macrodimers are as long-lived as they can. They decay when the Rydberg atom decays, so to say, yes? Okay. We can also see them, of course, and I show you the same picture, just a little bit larger, that you have seen already. And now you see basically we have here two missing atoms next to each other on the diagonal. This is the reconstruction. So what you see here, we excited basically a macrodimer here, 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 and you see it's like 4 to 1 for one direction against the other. What we did actually is we had this laser from the diagonal, and we had a polarization that was in plane. And the in-plane polarization in this case is, with respect to this molecular axis, a pi polarization. And I'm going to show you in a minute that this is basically very important to understand the symmetry here. And so we can also calculate now correlation function if you don't like the counting algorithm, counting argument. So you see basically what is basically under which distance from the origin, when we have a missing atom here, do we find another one? Then we find it predominantly along 1, 1, so one higher, one higher in x and y, and that's exactly the signal. So now let's see if we can control that molecular orientation. So the situation is always lattice diagonal and a lattice laser from here and polarization in plane. And now we are here. This was the same picture as I showed, is on an even vibrational line. Let's stay on an even vibrational line. Okay, we changed it, doesn't make a difference, and switch the polarization to vertical. You see, we lose fully directionality, and we excite those Rydberg macrodimers now on that line with this polarization in both directions. But now do something that seems like almost no change. Go from the 12 to the 13 line, keep the polarization as here, and we flip the direction of these macromolecules. So how can we understand that? For that, we have to look a little bit into the detail of the macromolecular wave functions that we have there. First of all, this is an avoided crossing between two different electronic states. So that's why this one is red on this side, blue on that side. And second, that's what we have is that basically gives us contribution of two electronic states, and the vibrational eigenfunction of each macrodimer is basically a superposition of those two. This gives us now basically two paths. We can couple here, and we can couple here, and we can have destructive and constructive interference. So the coupling strength, basically dipole operator, two-photon dipole operator with this wave function gives us the expression for the photo association rate to this one. So it has this electronic contribution that comes from the electronic dipole operators, the Rabi frequencies, and it has a Frank-Condon contribution that comes from the overlap of the wave functions. And all of those are important. So this is the same formula. Let me call the Frank-Condon factors F nu, and let's understand this change from the even to the odd vibrational state. So what happens here is basically this is the state contribution, so of the 35 p1/2 and the 1/2 3/2 states across space, basically across the well. And now something interesting happens, of course, for the odd states now, because take the example of this blue one. I weight, for example, the left-hand side here negatively, where this ratio is, where the value is high, and I weight the right-hand side positive, where the value is lower. So here, basically, for these ones, I get a relative sign between the red and the blue one, because this argument that I just made just turns around for the red one. So this one will be positive, while this one is negative, or the other way around, because, of course, this sign is kind of arbitrary. For the electronic path, Now we have to look at the polarization. If the electric field is in plane, so that's what I just said, we effectively have pi light, and that gives us a different excitation path to the final state than the case where we have sigma plus sigma minus light. That's when the molecular axis is basically in the other direction. So all of those are actually important, and we can evaluate all those factors. And so we have two different spatial symmetry conditions, so either even or odd vibrational numbers, and you see that basically changes here. My pointer is dying. That basically changes here the relative sign in the Frank-Condon part. And depending on if we have pi or sigma light, that changes the relative sign in these electronic contributions. And now we basically can just look at those signs, and we find basically that in the case of even vibrational levels, we get destructive interference on the sigma plus sigma minus light. That means basically the molecular axis in laser direction interferes destructively. That's why you don't see anything here. And in the other case, basically, where we have an odd line, the situation exactly changes, and we get constructive interference there. So that explains basically the orientation of those molecules. There's more. Jörg just told you about some multi-order correlations. I'm going to tell you about multi-order interactions. So if you look again at the spectrum looks nice and regular. Now I have to talk here more and describe, above 250 megahertz detuning, but around this 200 megahertz, there seems to be clearly an irregularity. And the question is, what's going on here? And if you now just calculate the dipole-dipole potential, and here I have to really give credit to the colleagues from Stuttgart, Hans-Peter Büchler's group, that have this open source calculation program for Rydberg pair interactions, which works beautifully. So the dipole-dipole doesn't show a specific feature. We can add now dipole-quadrupole terms, and you see a gap, an avoided crossing adds here. And then actually this avoided crossing jumps quite a bit up if we add quadrupole-quadrupole, and this quadrupole-quadrupole opening here is actually then required to explain the spectrum that we see here. So we directly see here really qualitatively, you know, you could sit your laser here and you would have a line or not a line, depending on if we take this quadrupole into account or not. So this is not a small contribution. That is really, you can build a switch of that if you like, if you would have quadrupole or not quadrupole terms. Okay. Oops. So this system is quite surprising, I have to say, in the lab, and I show you that there's a bit more. So if we actually excite, sometimes we see images like that. So you see basically there's a whole line of atoms missing here, or there's a whole line of atoms missing here. So there are cracks in the atomic array. So what's going on here? The honest answer is we don't fully know, but what we understand, something that's quite likely at the moment. And we know the cracks, they happen on the lines down here, basically. So, and now we have actually an accidental coincidence here, and that is basically, for that I have to explain that to you, I have to show you the excitation spectrum. So we go ground, Rydberg, detuned, and then to the upper well in a true photon transition. So this is well detuned to go to the upper molecular states. But now there was also this lower part of the avoided crossing. And it happens to be that for our parameters, it is roughly exactly half of the detuning we have to the lower one than we have to the upper one. So if we are two photon resonant here, we are actually single photon resonant for a configuration where you have two Rydberg atoms here and a ground state atom here. That means basically we have a seed, molecular seed, and then we have here a single photon resonance, so it goes very quick that we get these cracks. So that's at the moment our idea for this one. And this can actually be checked experimentally by changing the Rydberg state, where we change basically this accidental coincidence of these detunings here. Okay, with this I'm already a bit quick coming to the end, and I want to highlight the team that did the work. So everything is done in Immanuel's group in Garching at the MPQ, and the main people from our Rydberg team to acknowledge here is basically Johannes Zeyer, Simon Hollerith, PhD student, Johannes's postdoc, also Jun, he's here as postdoc and involved in the Rydbergs. Tony, not so much in the Rydbergs, he's also here, he's more on the many body localization side that I haven't talked at all today. So it's actually an experiment that we can share between two completely different lines of research. And very important here, Dan was visiting for some months. And he had like great contributions discussing all of this and understanding what was going on. And then we have theory support from Thomas Kohl's group in Aarhus. It was not my last slide. I want to finish with the summary and outlook. So I hope I convinced you that actually this ground-state atoms in optical lattices might actually be interesting for more than, well, let's say just quantum simulation, and actually also interesting for few body physics. And I've shown you an example where we basically observed and controlled dipolar Rydberg macrodimers. And the question is what we do with this, and you know, we usually have still the many-body head on, so our idea is always what do we do with this in context of many-body a little bit. So one idea, actually from Dan, is, well, you know, if we basically kill all atoms that are under this, that have this condition of being on the diagonal, we might be able to make nice dissipation stabilized many-body states by using basically the Zeno effect here. And we tried the toy version of that. There's no dynamics yet, the atoms are frozen, but basically we prepared an initial density pattern where we don't have diagonals and scanned over these molecular lines, and guess what happens? Well, we don't see any of those lines. So that one can avoid very nicely this loss mechanism there. Another idea is, of course, this is a molecule that has a different electronic state contribution on the left-hand side and on the right-hand side of the potential well. And this is actually a different Rydberg state that one in principle can detect. So we could prepare, for example, a wave packet, so a superposition of all of those, and let it oscillate, and by just looking at the Rydberg state contribution, see directly the molecular oscillation in this well. Another idea, and the last one, that has to do with now fully coherent many-body dynamics. That's basically the idea to use now this very narrow and kind of resonant enhanced molecular lines to couple near resonant to those lines and to transfer, well, basically virtually couple those two atom character to two ground state atoms, and with this very localized in space and also directional transfer down the Rydberg-Rydberg interaction by Rydberg tracing, so that's what we call this off-resonant coupling, and get by this basically well, let's say exotic, spatially exotic interaction structure in the ground state. And we did a lot of experiments along this line, along the Rydberg tracing line, where we don't use molecular states up there, but just basically the normal van der Waals asymptote, where we basically created an interacting Ising chain which showed collapse and revival dynamics to hook up on Jörg's talk for up to something like 10, that's 5, but we have more, something like 10 inverse effective spin interaction times. Okay, I think with this, I want to thank you for your attention, and I'm ready for questions.